Hi everybody, today we're going to talk about the multivariate normal distribution. Um, if the n-dimensional vector x is a multivariate normal with mean vector mu and covariance matrix sigma, then we write x is multivariate normal with, yes, it's just by definition, just notation, right? Mean vector mu and covariance vector sigma. The PDF of x is given by, so this is the probability density function, right? The one that's integrated. So this is the determinant of sigma, and then we're taking the square root of that, and then we have 2 pi. So the for one variable, the PDF of the normal distribution looks like this: 2 pi sigma, and then square root, and then so you can see there's like n of these. We have n normal distribution, and then this is again going to capture that we have n of them, and then here we have this at the top here. Usually with one variable we have divided by sigma squared, but now instead we have the inverse of the covariance matrix. Standard multivariate normal has mu equals 0 and sigma equals in, where the in is the n by n identity matrix. In this case, the xi's are independent. At this time, the professor launched into a proof. Let me check. Yes, launched into a proof of why this is the case. So if the covariance matrix is just the identity matrix, then this goes away, and this goes away, and we just end up with a multiplication of 1 over square root of 2 pi e to the x minus mu over sigma squared across all n, and that's why it's independent, because the PDF is just all the little PDFs of each of the normal random variables multiplied together. Okay, the moment generating function MGF of x satisfies phi of x of s is equal to es transpose of x is that. So I didn't know what a moment generating function of x was, so I'm going to go into it. So let me take a little bit of space here, and I'm going to use t because I learned it in t. So this from now on, let's just think about it in terms of t. Okay, so the idea of the moment generating function is it's supposed to be a way to determine if two random variables, or if two, so if the moment generating functions of two random variables are the same, then that means the random variables are the same. So it's supposed to be like a characteristic sort of function that uniquely identifies it. So how do we know that? So let's take this definition, which is this one, e to the tx, and I mean here it's transposed. So in this case, down here, what we've done is we've calculated it by replacing x and finding out this expression. But it turns out that there is a way to come up with infinite series representing this, and I might get it wrong, but it's something like 1 plus 1 plus, I forget, x plus x squared over, let me check, let me e to the power of tx, Taylor series. Is it called Taylor series? Yes. X squared. Yeah, I got it right. X squared. Sorry, it's 1 plus x squared over 2 factorial plus dot dot dot, like this. So then, by linearity of expectation, we can say this is equal to 1 plus expectation of x plus expectation of x squared divided by 2 factorial, and so on. And so now we have this function here that's equal to this. And now if we know another form for this, which we do right here, we can take the derivative of both sides to find out what the, this also should be expectation, of t, or not of t. T probably, where does it start? Yeah, no, t, there's a t here, and then there's a t squared here, and so on, because there's a t in the original one. So then, yeah, we take the derivative of both sides, and any order derivative. So let's just say we wanted to find out what this e, the x was. Let's take the derivative of both sides, so we end up with d phi x t dt is equal to ex. So this one goes away because we took the derivative, x plus the rest. And now let's evaluate this at t equals 0. And that's how we end up with a value for e to the x, because all the other terms cancel away because there's a t in front of them. So now we can find this out. And then we can take the derivative any number of times, and we can find out the value of expectation of x squared, and so on. And so that's, knowing that, I guess, determines uniquely determines the random variable that we have. So that's why this moment generating function is important, because we can take the derivatives of this function to determine infinitely these values, expectation of x squared, etc. Okay, the multivariate normal distribution 2. Recall our partition of x into x1, so we're partitioning our big random variable x into a part of them. Basically, what he's done here is he's just split it up into two. So then we have mu1 and mu2, and then we have covariance matrix. This is probably just, I don't know, there is a covariance matrix, so this doesn't have to be the identity, right? It's just the covariance matrix of 1 1 and then 2 2, and then I think it should be symmetric. I think these should be the same. Okay. Are the mean vector and covariance matrix of x1, x2. Then the following result on marginal and conditional distributions of x. The marginal distribution of the multivariate normal random vector is itself normal. So we're taking a marginal, so we can take, for I equals 1, 2. So we can take one of these and find the marginal distribution, and then it will be normal. That's what it's trying to say, the result. Okay, so then this is a graph that he showed of a bivariate normal PDF. So I wanted to look up what it looks like. So here, what does an uncorrelated and a correlated normal look like distribution? So here, if it's uncorrelated, we're going to have, so there's going to be a lot more points here, right, and then less points here. And then since it's uncorrelated, there's going to be it's going to go up here, and it's basically just going to be a circle with the most points in the middle, and these, like that. So it's like a hump in 3 dimension. There's going to be a lot of points here. The PDF, I mean, there'll be lots of points. We can also represent it as a probability, but that it's uncorrelated. Therefore, you can have equally likely that a point here, if you have this, if you have a point here, it's equally likely that it's, well, it's not equally likely, but it's just uncorrelated. I don't know, it's very hard to explain. Meanwhile, in the correlated case, for all state or simulations, if you have a higher value of x1, then you're going to have a value, it's very likely that you will have a higher value of x2 as well. So therefore, for all points, they're more likely to just sort of follow this pattern, sideways like this. I mean, there'll still be most points here, but it's going to look like this. Okay. Conditional distribution. Assuming sigma is positive definite, the conditional distribution of a multivariate normal distribution is also a multivariate normal distribution, in particular this, where the mu is equal to this and the sigma is equal to this. Notice that this is subtraction. So the idea that he talked about behind this is that if you have a, okay, so if you have an uncorrelated, this is not something you mentioned, but if these two are completely uncorrelated, then the x2 given x1 is just x2, right? Just thinking about it. But if they are correlated, then knowing information about x1, your variance is going to go down, because now you know some information about x1, which helps narrow down the x2. So if you have x1 over here, and I'm going to draw the graph of a correlated, at least positive correlation, normal distribution, then if we know that x1 is here, is this value, then the variance of this is much smaller than the variance in general of x2, or yeah, of x2. Yeah, because x2 can be any of these values, but if we narrow it down here, then it's a much smaller set. And this holds true for any x1 you pick. So that's it. See you next time.